Okay, guys, let's pray. Father God, we thank you, Lord, for this day. We praise you, Father God, for your goodness, Lord God, in our lives, Lord. We pray, Father God, you just bless this time, Lord God, the students, Lord God. I just pray, Father God, you just put your hand of protection over them, Father God. Give them peace, give them comfort, give them joy, Lord God, in you, Lord, no matter what the circumstances or situation might be, Lord God. I just pray, Father God, right now for your love to just shower over them, Father God, for them to feel your presence, Lord. Pray, Father God, you give me the words you have me to speak, Lord. Give us all listening ears, Lord. In Jesus' name, amen. Well, welcome, guys, to numerical analysis. We're going to jump into it, section 5 point. Oh, well, actually, what section are we in? Numerical integration. And that is section 4.3. Section 4.3 is what we're going to be this time around. I said 5.3, 4.3. Numerical integration. Numerical integration. I'm going to change markers here. Topics for the day. We're going to be looking at left endpoint method. Trapezoid method. And Simpson's method. Okay. All right, so we have left endpoint method, trapezoid method, and Simpson's method for doing numerical integration. Right, last chapter we focused on, or last couple of sections, we focused on how to differentiate numerically, right? Focus on that concept, the idea of finding the first and the second derivative, but we can even find the third derivative and so forth. And now we want to look at the kind of the opposite of that, finding the antiderivative, or actually not antiderivative, but be able to integrate numerically. Okay. And so let's start off with these methods that we have here. So we will approximate the definite interval from a to b of f of x dx. And we will approximate the definite interval from a to b of f of x dx. This is called numerical integration. Numerical integration and to approximate the definite interval, right? We're going to approximate the area, the definite interval of polynomials. So I want to say that here. Couldn't talk for a second there. So to approximate the definite interval, A to b of f of x dx, we approximate. We find the definite interval of interval from a to b of p of x dx, where f of x is approximately equal to p of x, and this guy's our interpolated polynomial. Right? We dealt with Lagrange polynomials, right? Splines, and we can integrate using the spline or Lagrange polynomial or Newton polynomial. We're going to use a Lagrange polynomial to approximate the interval from a to b of f of x dx. So to approximate the interval from a to b of f of x dx, we find the definite interval from a to b of p of x dx. Let's look at an example. Well, before we look at an example, we will approximate the integral from a to b of f of x dx using, a, the 0th degree Lagrange polynomial, which is going to be the left endpoint method. Before I go to the first and second, let's approximate f of x, the integral from a to b of f of x dx using the 0th degree Lagrange polynomial. Okay. Now, suppose I have a function from a to b. Let's just suppose it's above the x-axis, right? Now, the 0th degree Lagrange polynomial is going to be the polynomial that only uses one point, right? One value in an interval from a to b. For example, let's just use this value. We can call this, let's call a and b x naught. This will be x naught and this will be x1. Okay. And this will be a distance of h, right, between these two. And I can say, okay, my 0th degree Lagrange polynomial is just going to be one function value. It's going to be a straight line, essentially. It'll be p of x is equal to, I'll just say f of x naught. P of x is equal to f of x naught. That's a 0th degree Lagrange polynomial. So when I draw this, right, this is just a straight line. So this is my 0th degree Lagrange polynomial right here, p of x, which approximates my function f of x here. And I'm going to look at the area underneath that guy, and that'll be my approximation. Look at the area underneath that. Well, what is the interval from a to b? Or I could say x naught to x1 of p of x dx. Well, you guys are pretty smart, right? You know that's going to be the same thing as f of x naught times x1 minus x naught. Or I can say f of x naught times h. So the left endpoint method, right? Essentially, I think of this as the height of my rectangle times the width of my rectangle, right? So f of x naught times h. And this, since I'm using the left endpoint of my interval, we call this the left endpoint method. And I got it using, I was able to figure this out using a 0th degree Lagrange polynomial. You're like, well, this is not a very good approximation, Dr. Wesley. Can we get a better approximation? I'm like, sure. Let's increase our degree. Let's use that 1st degree Lagrange polynomial. And this is going to yield the trapezoid effect. Let me try this again, right? So let me draw a picture. Here's A and B. I can really call it x naught and x1. And let's just call it x naught and x1 from now on. And what we mean by x naught and x1 are just A and B. Okay. I have my function. And to be able to find the first degree Lagrange polynomial, I need 2 points, right? I need 2 points to be able to approximate, to be able to come up with a first degree Lagrange polynomial. And the 2 points I'm going to use are going to be these 2 points right here, f of x naught and f of x1. And they connect together as a line. So here's my p of x again. What does p of x look like? Right? If you guys remember the formula for the first degree. We have what? P of x is equal to f of x naught, right? Times x minus x1 over x naught minus x1 plus f of x1 times x minus x0 over x1 minus x0. Now, what I'm going to do is I'm going to integrate this polynomial that I have over the interval from a to b. Now, when we look at this area underneath this function, we notice that the shape we get is a trapezoid. Trapezoid shape. And this is why this is called the trapezoid method, right? Because we get this, when we look at the area underneath this polynomial, you get a trapezoid shape. And when we integrate this, integrate x naught from x out to x1 or p of x dx, okay, we're going to end up with f of x naught, I should say f of x1, minus f of x naught times h divided by 2, where h again is this distance between x naught and x1. H is my distance between x naught and x1 in this case. So far we have a formula for finding the area using a 0 degree Lagrange polynomial, right? I can approximate my area of my function by f of x naught times h. I can approximate my area underneath my function using a first degree Lagrange polynomial, right? And with this formula. And I'm going to be able to approximate the area underneath the curve using a quadratic polynomial. So we need to do a second degree. Oh, I apologize. That should be a plus between these two guys. So this should be f of x1 plus f of x9 times h divided by 2. That's going to be a plus between those two guys. F of x1 plus f of x9 times h divided by 2. And the last one is c. Second degree Lagrange polynomial. And this is going to yield Simpson's rule. It's actually called Simpson's 1/3 rule. You'll see why in just a second. So again, suppose I have a function. Okay, so I have from a to b, right? But before I put down from a to b or x naught to x1, how many points do I need to be able to approximate a to be able to come up with a second degree Lagrange polynomial. How many points do I need? I need 3 points, right? I need to have x naught, x1, and x2. So what I'm going to do is I'm going to actually put a point that's in the middle. So I have x naught, x1, x2. Okay. And I'm going to approximate this with a quadratic equation. Oh, it didn't go to those points. Got to make a quadratic equation that goes to those points. So maybe something like this. Okay. I want to look at the area underneath. Yes. What I want to look at. Let's put that in our second degree Lagrange polynomial. Second degree. You guys remember this one? So this will be P of x is equal to f of x naught, right, times, in this case we're going to have x minus x1, x minus x2, over x naught minus x1, x naught minus x2, plus f of x1, right, times x minus x0, x minus x2, divided by x1 minus x0, x1 minus x2, plus, our last guy, f of x2 times x minus x naught times x minus x1 all over x2 minus x0, x2 minus x1. Whoa, that's big. But just like we did with the 0th degree and the 1st degree polynomials, we're just going to integrate this guy over the interval from x naught to x2, right? We're going to integrate this polynomial over the interval from x naught to x2. P of x dx. And when you integrate this integral, this polynomial over the interval of x naught to x2, we get 1/3 times, and I'm going to use square brackets this time, the quantity f of x naught plus 4 f of x1 plus f of x2 times h. And the reason why it's called Simpson's 1/3 rule is because I have a 1/3 that's in front of my entire bracketed expression here. So let's put them all together and do an example. So that you have them all in your notes together. Right? So if we do that, I have left endpoint method. Here I can say that the integral from a to b of f of x dx is equal to, it's approximately equal to, f of x naught times h. For the trapezoid method. Like I said, the integral from a to b f of x dx is approximately equal to h divided by 2 of f of x naught plus f of x1. And then Simpson's method. Simpson's 1/3 rule, actually. We have that the integral from a to b of f of x dx is equal to h divided by 3 of f of x naught plus 4 f of x1 plus f of x2. Yep. Right? These are our guys. Let's look at an example of how we can use this. I want to compare the left input, trapezoid, and Simpson's rule, or Simpson's method. Simpson's rule, rule. It doesn't matter. Method, rule, I had rule before. I don't know why I changed it to method up there. To approximate the integral from 0 to 2 of x squared dx. Now I know that x squared dx, that x squared is a polynomial, so it should be an easy approximation for these guys, right? Because all of these approximations are based on polynomials, right? The left input method is based on the 0th degree, trapezoid method is based on the 1st degree, and the Simpson method is based on the 2nd degree polynomials. But I still want you guys to see it. Using h equal to 1. Using h equal to 1. Okay, so I'm going to use h equal to 1. So that means I'm going to have to break this up into 2 problems, right? Because I'm going from 0 to 2. All right, I have this polynomial y equal x squared. And when I approximate the area underneath this guy, I'm going to do area. By the way, what is the area for this? Those of you guys who know, all of you guys who know, said 1/3 x cubed from 0 to 2, so that's going to be 8/3. 8/3 is about, what's that, 2.6666 forever. So let's see how well our approximations do. Definitely Simpson's method should approximate this guy exactly, right? Because Simpson's method is based on the 2nd derivative, and x squared is a 2nd derivative. Simpson's method is based on the 2nd degree polynomials, right? X squared is a 2nd degree polynomial. I apologize, guys. It's a 2nd degree polynomial. So let's start with the first one. Left input method. With the left input method, I really had to break this up into 2 parts, right? H is equal to 1, so 0 to 1 is going to be my first approximation, and then from 1 to 2 would be my second one, right? So I can say from 0 to 2 of x squared dx is approximately equal to if I look at this as my first interval, right, from 0 to 1, the left endpoint of my first interval is going to be 0, so I have nothing there. And then from 1 to 2, my left endpoint is 1, so I have a little rectangle right there. But regardless of the situation, I know that I'm going to have f of 0, right, times 1, right, because f of 0 is my left endpoint times 1, which is my h, plus f of 1, right, which is my second left endpoint times 1. What do we get when we do this? We'll work this out. This is 0 plus 1, so I get 1. Right, you guys have seen this before in calculus many times, so you're like, what do you do? That's not amazing, Dr. Weston. I understand. Let's go to the trapezoid method, or trapezoid rule. Oh my goodness. It doesn't really matter. Method rule, trapezoid rule, that endpoint rule. Okay. I'm going to iterate from 0 to 2 again. X squared dx. Now for this one right here, I'm going to be using this one. My h is still 1. Doesn't change. 2 times. Here, we have to break this guy up again, right? Because we have to choose a left endpoint and a right endpoint for each one of my intervals, right? That's how this works. I need a left endpoint and a right endpoint. So here I have f of, in this case, it was f of x0, so f of 0, plus f of 1. That takes care of that guy. That takes care of my first interval, and then I need to do another one for this one, right? So I have another plus 1 half. F of 1 plus f of 2. Okay. So that takes care of that. If I were to draw a picture right here, it's 2, it's 1, it's 0. My trapezoid method is going to do something like this. Look at the area here, and then from here to here. Look at the area here. So I have these two guys here. That's going to be a much better approximation than the last one we had. So we plug in, get 1 half, say 0 plus 1, plus 1 half of 1 plus 4. I believe that's what it is. And what does that work out to be? So when we do this, I get, when I plug this in, what's that, 9? Is that 9? Yeah. Nope. It should be 9. It should be 3. Oh my goodness. 3 is what I get. It's still overestimated, but you can kind of see that from the actual graph, right? That we're going to be a little bit above 2.6666 in this case. In Simpson's rule, okay. So I have my 3.0, 1, and 2. Okay, just like this. That's not a very good 1. 1. Okay, suppose like that. is still going to be 1, right? However, I have my 3 points, 0, 1, and 2. I need 3 points for Simpson's rule, so I'm just going to use all 3 of those points. So this is going to be, so I'm going to go from 0 to 2 f of x squared dx. Okay. That's going to be h, which is 1 in this case, still 1, divided by 3 times f of x naught. F of x naught is going to be my first value, right, which is going to be 0, plus f of x1, which is going to be f1, f of x2, which is going to be f2. Now, since this is based off of the Lagrange, second degree Lagrange polynomial, right, this guy should line up perfectly. Just get it, knock it out of the ballpark. So what do we get when we do this? We get 1/3. This is going to be 0 still, plus 1 plus, what's that, 2 squared. Did I do that right? Oh, this should be a 2 in between, right? 4. There should be a 4 in here. 4. There we go. That makes me happier. So 4 times 1 is 4. Plus, this is going to be 4 here. And that gives me 8/3, which is exactly what I want to see. Right? And so I get the exact area, right? So this, my actual value was 2.666 or 8/3, right? Simpson's rule gave it to me exactly because, of course, we're approximating x squared with a quadratic equation, a quadratic polynomial, so of course that's going to work out. Okay, so let's look at something else here. We can actually think about, we have the 0-degree polynomial, we have the 1st-degree polynomial, that and 2nd-degree polynomial. That's how we got left endpoint method, trapezoid method, Simpson's method, right? So we've had all these. We can actually extend this idea. So the left endpoint method is for a Lagrange polynomial of degree 0, right? This guy is of degree 1. Where we got this from? This guy is of degree 2. Where we got this from? But what if you want to go to degree 3 or degree 4, right? Lagrange polynomial. So we have, I want to just introduce you to 2 more. We have Simpson's 3/8 rule. Okay. And this one is for a 3rd degree. So we have x naught to x3, f of x dx. So if I wanted to think about this, I could think of this one from x naught to x1. So let's just kind of change it so we have that. We can make it change it of x naught to x1. This is x naught to x1. This one really goes from x naught to x2, right? This one, when we go to the 3rd degree, right, we have to add 1 more point, right? So we, instead of having x0, x1, x2, we need to have another x3 for the third degree polynomial. So it goes from x0 to x3, f of x dx. And that guy is approximately equal to 3h over 8. That's where we get that 3h from. F of x naught plus 3 f of x1 plus 3 f of x2 plus f of x3. Okay. This is our guy. And this is Simpson's 3/8 rule. And we have, and this is for a third degree Lagrange polynomial, right? So let's go to the third degree. And fourth degree Lagrange polynomial will yield this one. This is called Milne's rule. For degree 4 Lagrange polynomial. Okay. And that one is from x0 to x4, right? If you keep track, f of x dx, which is approximately equal to 2h over 45 7 times f of x0 plus 32 f of x1, 32. So 7 f of x0 plus 32 f of x1 plus 12 f of x2 plus 32 f of x3 plus 7 f of x4. Okay. And so this is the approximation of my definite interval of f of x, right? Using a fourth degree Lagrange polynomial. Let me give you an example of how good these guys are, and then we'll talk about the error of the left endpoint trapezoid and Simpson rule. All right. Left endpoint trapezoid, Simpson, and so the first one is Simpson's 1/3 rule. 1/3 rule. This is Simpson's 3/8 rule, and this is Milne's rule that we have here. Let's just look at some examples real quick. I'm going to approximate. The integral from 0 to pi over 4 of sine of x dx using the 5 approximations. So I'm going to use the left endpoint method, trapezoid, Simpsons, so on and so forth. Now what I'm going to do is I'm going to do something a little bit different from what I did before. I'm only going to break up my interval if I have to break it up, right? For instance, for the left endpoint method, I don't really have to break it up into 2 parts or 3 parts. I can just go from the last value, which is the first value, which is 0, to the last value, which is pi over 4. The same thing for trapezoid method. I only have to plug in the first value and the last value. However, for Simpson's method, I need to break it up into 2 parts, right? So I'm going to split this up at pi over 8 for this one. Okay. And for Simpson's 3/8 rule, I have to split this up into thirds, and for this one, I have to split it up into fourths. Okay. So that's what I'm going to do for this. So I'm going to handle it just a little bit different from the way I did the last one. So let's look at the left endpoint method. My h is going to be pi over 4 because I don't have to split the interval up to be able to apply the left endpoint method. So when I do this, I say 0 go to pi over 4. Sine of x dx is approximately equal to f of 0 times pi over 4. What is sine of 0? I actually put sine of 0 because that's my answer. Sine of 0 times pi over 4. Sine of 0 is 0, so I need 0 for my answer. Okay. For the trapezoid method, or rule, you choose. Again, I'm going to choose my h to be power 4 because I'm not forced to split up my interval to be able to approximate it. I have from 0 to power 4, sine of x dx is approximately equal to. Here I'm going to I have pi over 4 divided by 2. Pi over 4 divided by 2. Okay. Times f of 0, which is going to be sine of 0, plus f of 1, f of power 4, which is sine of power 4. And when I plug that in, I get 0. What do I have here? 27768. I'll stop there. 0.27768. I'm going to do Simpson's method. Now with Simpson's method, like I said before, with Simpson's method, I need to have 3 points between from 0 to power 4. So I need to incorporate another point, which is pi over 8, which is going to split this up into 2 separate, it looks like 2 separate intervals, but I'm integrating over this entire interval from 0 to power 4. So my h in this case is going to be pi over 8. So for Simpson's method, my h is pi over 8 because I have to split it to be able to integrate from 0 to power 4. I'm forced to split it to be able to integrate from 0 to power 4. So when I do that, my h is equal to pi over 8, so I get 0 to pi over 4 of sine of x dx is equal to. Here I'm going to have, looking at our formula, pi over 8 divided by 3 times sine of 0 plus 4 sine of pi over 8 plus sine of power 4. And when I do that, what do I get for Simpson's 1/3 rule? I get 0.29293. I'll say that. Right? So that's what I get for this Simpson's 1/3 rule. What about Simpson's 3/8 rule? Let's put it up here. Now, how many pieces do I have to split this one up into, right? When I do Simpson's 3/8 rule, right, I have to split it up into 3 pieces, right? Here I divided, essentially I divided the interval by 2, right? Get the pi over 8. So I need to divide it by 3. So I get, if I were to think about it like this, right? For Simpson's 3/8 rule, I need to go from 0. So that's going to be pi. If I divide by 3, I get h has to be pi over 12, right? Something like that. So this is pi over 12, 2 pi over 12, and then 3 pi over 12. By the way, 3 pi over 12 is pi over 4. To be able to use Simpson's 3/8 rule on the interval from 0 to pi over 4, right, I have to divide my interval up into 3 pieces. Right? So my h is pi over 12 in this case. Right? Like I said before, with the left input method and the trapezoid method, I really didn't have to split it up at all. I did that in the last problem because I wanted to get a better approximation, but I didn't have to do that, right? I could have just said, I'm just going to go from the interval from 0 to power 4. That's going to be my approximation. And that's what I did in this case for the trapezoid and left input method. For Simpson's method, 1/3 and 3/8 and mils, I have to split it up to be able to do anything on the interval from 0 to power 4. So h is equal to power 12, so I have an interval from 0 to power 4. Sine of x dx is equal to 3 times pi over 12 h sine 0 plus 3 sine of pi over 12 plus 3 sine of, what's that, 2 pi over 12, which is pi over 6 if I wanted to. I said pi, I was just do 2 pi over 12 just to be consistent. And then the last one is plus sine of, I'm going to write pi over 4. Okay, just so we know that we finish. So, when I evaluate this one, I get 0.29291. That's what I have there. 0.29291. Okay. And finally, we have Milne's rule. Okay. So this is Simpson. Oh, I never said this is Simpson's 3H rule, right? And then this is going to be Milne's rule or method, whatever. We need to divide this up into 4 pieces, right? So take pi divided by 4 and divide that by 4, so we get h is equal to power 16. So we're looking at these values: 0, pi over 16, 2 pi over 16, 3 pi over 16, 4 pi over 16. 4 pi over 16 is pi over 4. So my h is pi over 16 in this case. So if we were to integrate this from 0 to power 4, sine of x dx, this is going to become 2 times pi over 16 divided by 45 times 7 sine 0 plus 32 sine, what's that, pi over 16 plus 32 sine of 2 pi over 16, or pi over 8, plus, I know, 32 sine of 3 pi over 16, plus 7 sine of pi over 4. And what do you get when you do that? You get this to be about 0.29289 essentially. Right, and it actually has more decimal places than that, of course. What's the exact answer? Up to 5 decimal places. Up to 5 decimal places, the exact answer, up to 5 decimal places. 0 to power 4 of sine x dx. I have it to be 0.29289. Right? So Mills' rule came out the winner, of course, right? It's going to have a higher degree of Lagrange polynomial, so it's going to give us the highest accuracy here. But notice that Simpson's rules are not that terrible. Trapezoid rule is not that bad. And if we can make h smaller, right, instead of just going over the entire interval, if we had broken it up as h equals pi over 16, right, we probably would have got a pretty good approximation, right? So instead of just going over that entire interval, right, why not just split it up like we did the first time? So split it up into like let h equal pi over 16 and do that. And we might get still a decent enough approximation. And that's what we're going to talk about next, right, about how we can essentially do a sum of these approximations over an interval, right? So we split our interval up into pieces, and then we take the sum of those, all of those approximations together to get our final approximation over my bigger interval that I'm looking at, right? And that's going to be a composite, the composite rules. And we're going to do those in a little bit. Before we do the composite rules, I want to talk about the errors for the Simpson method and left endpoint method and the trapezoid method. I'm not going to talk too much about the errors of the other two, Simpson's 3/5 and Mills rule, but the first three that we have here. I'm going to erase this part. Get my right paper here. Actually, let's talk about those errors for the composite version of that, right? So I'm getting ahead of myself. Let's talk about the composite, what I was talking about before, by essentially breaking our interval up into smaller sub-intervals and approximating those intervals, definite intervals, using these like mini approximations. So let's do that next. Let's talk about the composite rules. Approximating intervals. So we're going to put down the left endpoint composite rule. Okay. And this is what you guys have seen in calculus 1. Like I said, the integral from a to b of f of x dx is approximately equal to the sum I equals 0 to n minus 1 of f of xi times h, where h is equal to b minus a divided by n. Okay, you can think of a as being my x naught, b is my xn, right? I'm breaking it up into pieces. And as what we've seen before in calculus, where I have some function from a to b, I break this up into sub-intervals, and then I approximate my area by looking at these mini approximations. Okay, so this is what we call our compositing, kind of a summing together of our left endpoint rule. Okay, so that's the left endpoint composite rule. Let's talk about, and there is a error that actually comes with the left endpoint composite rule. So the error when we between the actual integral and the approximation, the error is less than or equal to the absolute value of b minus a divided by 2 times f prime at z times h, where z maximizes f prime. On the interval from A to B. All right. Now we have the trapezoid rule. Trapezoid rule. So we have the trapezoid composite rule. Trapezoid composite rule. And what does that guy look like? Let's put it down. It's the interval from A to B, f of x dx. This guy's approximately equal to, we have h divided by 2 times the quantity f of x naught plus 2 times the sum I equals 1 to n minus 1 of f of xi plus f of xn. Okay, so this sum I equals 1 to n minus 1 is only on the f of xi term. F of x0 and f of xn are outside of that. Okay. Notice that if n is equal to 1, then this term disappears, and we just have one interval that we're dealing with here. Again, where h is equal to b minus a divided by n, same thing that we did before. And we have an error less than or equal to the absolute value of b minus a over 12 times f double prime at z times h squared. Here, what we're going to do, z is going to maximize the derivative, second derivative of f in the interval from a to b. So it does the same thing that it did with the first derivative in our first attack. Notice that here my error is big O of h. This is for the left endpoint approximation. My error is big O of h. For the second one, for the trapezoid composite rule, my error is big O of h squared. So the trapezoid composite rule is better. Last one. We have Simpson's composite rule, or the composite Simpson rule, whichever one you want to say. So we have Simpson's composite rule, or composite Simpson rule. Words escape me today. For this one, for this composite rule, we have an integral from a to b of f of x dx. This guy is approximately equal to h divided by 3 of f of x naught plus 2 times the sum I equals 1 to n divided by 2 minus 1. Here we assume that n is an even number. So this n corresponds to, if we have x0, x1, x2, x2, that 2 would be even. That's what, so if I go from x0, x1, x2, x3, x4, right, that would be my 4 would be an even number. So that n would be even. So we're assuming that n is even. F of xi, f of x2i, sorry, plus 4, I know this is a big one, times the sum I equals 1 to n divided by 2 plus f of x of 2i minus 1 plus f of xn. Now this is a big one, and it's a lot of times we don't even use it. There's a little bit of a pattern to help you to figure out what you're supposed to do. And we're going to look at that in just a little bit. But this is the formula for the Simpson's composite rule. It looks like a beast. It looks terrible. It looks like Dr. Wesley, I don't want to do it. I don't want to do it. But it'll be fine. It'll be fine. You'll be okay. Where h is equal to b minus a divided by n. So same h that we had before. That doesn't change with this composite rule, right? Playing with by different rules. This time. Error. My error is going to be less than or equal to the absolute value of b minus a divided by 180 times the fourth derivative. Evaluated z times h to the fourth power. Times h to the fourth power. Where, again, z maximizes the fourth derivative in the interval from a to b. I know that's a lot to keep track of, but it's not that terrible. A lot of times we don't even use this formula at all. We just remember how the Simpson rule works. If you remember how Simpson's rule worked, right, the one that we did in the beginning, if you remember how Simpson's rule worked, the first problems we did, all they were doing is we're just summing up smaller versions of those, right, that we're subdividing on that interval. And then we're doing Simpson's rule on that particular set, and then we're adding all of those Simpson rules together. And this is just a way that your computer can do it a little bit faster, right? Because you can think of this as indexing into an array or something like that. That's not the way we're going to do it, or at least that's not the way I'm going to do it. I'm going to keep it simple because I'm a simple guy. Let's look at an example. Approximate the integral from 0 to 2 of x cubed dx using n equal to 6. And we're going to use the left endpoint approximation, the trapezoid approximation, and we're going to use Simpson's approximation, 1/3 rule. Here, n equals 6 means that we're going to make 6 sub-intervals, right? So n equals 6 means 6 sub-intervals. So we have x0, so we have x0, x1, x2, x3, x4, x5, x6, right? So we get 6 sub-intervals, 1, 2, 3, 4, 5, 6, what we get here. And I need this to be even because I want to be able to use the Simpson's composite rule. And I can only use Simpson's composite rule when I have an even number of values. Okay. Here, x0 is 0, and x6 is 2. What's my h in this case? H is going to be equal to what? 2 minus 0 divided by 6, right? Which is 1/3. So 1/3 is my h that we're going to use for all of these problems. 1/3 is going to be what we use for each one of these problems. All right. So let's look at the left endpoint, the positive function. And I can see that my integral from 0 to 2 of x cubed dx, this is really just going to be h times, okay? Because I have a h that's being multiplied, that I can really pull out to the front if I wanted to. See this h right here? This h is not a part of the series, and I can really pull it out to the front, right? And so it'll be h times the series I equals 0 to n minus 1 f of xi. Now the left endpoint approximation, I'm just going to be looking at the left endpoints. So let me draw a little picture here somewhere. Let me draw this one a little bit further down. Okay. And just imagine that this is x cubed. I'll put you into a little cloud. Okay. And I broke this up into pieces: 0, 1/3, 2/3, 1, 4/3, 5/3, and 6, 2. Oh, just imagine that is x cubed. That's a lovely x cubed. Beautiful. Beautiful x cubed. Just gorgeous. Right, when I break this up, I'm going to have 6 approximations, right? One from here to here. From 0 to 1/3, one from 1/3 to 2/3, one from 2/3 to 3/3, one from 3/3 to 4/3, one from 4/3 to 5/3, one from 5/3 to 6/3 of 2. Right, I'm going to have each one of these represents approximation. Right, my h is going to be the width of these guys, and I just pull that h out. My h is equal to 1/3, so let's write 1/3, right? Let's write it down. Well, let me not write it down. Let's write it down. I'll leave it alone for right now. I keep changing my mind on what I want to do. It's so hard to decide sometimes. Oh. Okay, so but I'll keep it like this. So it's h times, I have f of 0, right? That'll be my first rectangle height, plus f of 1, which will be my second rectangle's height, plus f of 1/3, which is my second rectangle's height, plus f of 2/3, plus f of 1, plus f of 4/3, plus f of 5/3, And that's my last rectangle, right? That's the height of my last rectangle is at 5/3, right? That's my last one. Notice I have 6 of these guys. So this is essentially width times height, width times height, width times height, width times height, right? So I'm just summing up all of these areas, right? You guys have seen this before. Just kind of reminding you. And let's plug in. So I get 1/3 times. If we plug in, I get what's it? 0 plus 1/27 plus I have 8/27 plus 1 plus, oh gosh, that is 64/27. And the last one is 125/27. And that works out to be approximately equal to, and I'm going to give it to you, and I put down all these fractions, I'm going to give it to you in decimal form. I get about 2.7777. And it repeats forever. So I can just say 2.7. It goes on forever. So there's my approximation using the left endpoint composite form. Oh, it'd be nice to actually know what in the world are. What is the actual answer here, right? What's the actual value of this interval? Let's find that out. So actual value. So an interval from 0 to 2 of, what was it, x cubed, dx. That's going to be what, 1/4, x to the 4th from 0 to 2, what is that? That's 16 divided by 4, that is 4. So this approximation that I had for the left endpoint approximation is not very good, right? 2.7 is not very close to 4. That kind of makes me sad. What about the trapezoid method, right? Trapezoid. Trapezoid rule. Again, I'm going to draw a little picture here. Okay, so this is 0, 1/3, 2/3, 1, 4/3, 5/3, and then 2. So we're doing the trapezoid method this time, right? And so essentially we're making these straight line approximations. Let's do this guy. Now notice that to be able to do the trapezoid approximation, just the first one, right, I need to use the point 0 and 1/3. To do the next approximation, I need the point 1/3 and 2/3, right? To do the third approximation, I need the point 2/3 and 1. And for the, so when I'm doing this approximation, notice that I'm using the interior points twice. Can you guys see that? The interior points, 1/3, 2/3, 1, 4/3, and 5/3 are going to be used twice when I do my composite approximation, right? The left point, the leftmost point, and the rightmost point are only going to be used one time. So let's look at it. So we have the interval from 0 to 2 of x cubed dx is equal to, it's going to be h divided by 2. Remember, in our first example that we did, it was f of x naught plus f of x1, right? So that's what we're going to do here. So this is going to be this plus this, right? We have this h divided by 2 that's on the outside. So this is going to be f of 0 plus f of 1/3, right? That takes care of this one right here. When I multiply h divided by 2 times this, it gives me the area underneath that line. But then I need to do it again, right? And then I have to do f of 1/3 plus f of 2/3. And these two guys multiplied times h divided by 2 will give me the area right here. Okay? And of course, I will continue doing that over and over and over again, right? Until I get to the very end. But I'm going to run out of space on the board. Can you guys see that? I'm going to run out of space. I need to condense this down. I know that these 2 points are being used twice, right? So why do I write them both twice? I should just do 2 times f of 1/3. So that's what I'm going to do. I'm going to go back and I'm going to say, okay, this is 2 times f of 1/3 plus 2 times f of 2/3 plus 2 times f of 1 plus 2 times f of 4/3 plus 2 times, and I still ran out of space, f of 5/3 plus f of 2. My f in this case, if you guys are wondering, my f is x cubed. It's my f, x. If you haven't figured it out yet, like, what in the world is Dr. Wesley getting his f from? Where is f? What in the world is f? F is my integrator. So guess what? Now you guys see where this 2 is coming from in the trapezoid composite rule, right? And you see this 2 is coming from the interior points that we have for our interval. And the left endpoint and the right endpoint of the leftmost endpoint and the rightmost endpoint are only going to count 1 time. So let's plug in and see what we get. So we get h, which is 1/3 divided by 2 times 0 plus I know what these values are already. I know what those values are already. I've seen those before over there. Right, we just did it with the left endpoint method. F of 1/3, F of 2/3, F of 1, and F of 4/3. I already know what those are. Actually, I know all the values. What I want to do is this 2 is multiplied times those guys. So we're just going to do 2 times all those guys that I have there. 1 over 27 plus 8 over 27 plus 1 plus 64 over 27. All those interior points are multiplied by 2 plus we have plus 125 over 27. Plus f of 2. F of 2 in this case is going to be 8. Now, I actually have to use f of 2 this time. Remember, because the trapezoid rule is going to use the left point and a right point. So that's why f of 2 is showing up here. And you know what I get when I do this one? I get 4.1111. It repeats forever, just like the other one did. This is a much better approximation. This is a much better approximation. It makes me happy, right? 4.111111 is much closer to 4 than 2.7 was. So I'm kind of happy about it. It's still an over approximation, but we can kind of tell that from looking at the graph that we're going to get that to happen. Okay. And let's look at our last one, Simpson's 1/3 rule. Simpson's 1/3 rule. And for this one right here, right, if we look at this guy, right, it's like, okay, all right, let's draw a picture. Zero, so here is x cubed, just imagine, just a beautiful x cubed, 0, 1/3, 2/3, 1, 4/3, 5/3, 2. To use Simpson's rule, right, I always have to grab 3 points at a time. So it's a little bit different. Here I have to grab 2 points, right, for trapezoid rule. Here I have to grab 3 points at a time. I grab these 3 points, right? Then I grab these 3 points. Kind of reminds me of a spline. Then I grab my last 3 points. So I got 3 points at a time. So I have essentially, I'm going to sum together 3 mini Simpson rules, right? A Simpson rule from 0 to 2/3, a Simpson's rule from 2/3 to 4/3, and a Simpson's rule from 4/3 to 2. That's what I'm going to do. And I definitely don't have enough time to put it here. I don't have enough space. My goodness, I don't have enough time either. Not enough time in the day, not enough space in the world. All right, so I'm gonna have to erase this. I don't want to erase this. I think I can erase at least this error part right here. Okay, I'm gonna erase this part too. I think I can squeeze it in here. I wanted to compare all 3 of these guys together so you can see them all on the board. Okay. So the integral from 0 to 2 of x cubed dx. Now, when we do this, right, and don't write anything down right now because I'm going to erase something in just a second. Okay? So don't write it down just yet. But here is my Simpson rule. We know from looking at Simpson rule before that we're going to have an h divided by 3 that I can pull out. You can think of that as kind of, and then I'm going to look at, I have these 3 points for the first one, right? We know that this is going to be f of 0 plus 4 times f of 1/3 plus f of 2/3, right? That takes care of this one right here. So it's going to be this times h divided by 3 will give me the area underneath this. Okay. Now, if I want to get the area underneath this part, right, this is going to be plus. Now I start with 2/3, f of 2/3, plus f of 1 plus f of 4 times f of 1 plus f of 4/3. Right? And I can keep going, but I noticed something again, right? What happens? These 2 terms repeat, right? This term right here repeats. So f of 2/3, f of 2/3, f of 4/3, and f of 4/3 is going to repeat right here when I do this one. Okay? And let me go ahead and write it out since it's already there. Plus 4 times f of 5/3 plus f of 2. Okay. But really, when I look at this, right, these guys, I just add these guys together. And we have this kind of alternating values where we have 4, 2, 4, 2, 4, 2, except at the endpoints. The endpoints are only going to have are just going to be multiplied by 1, right? So you have 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1, right? That's how it ends. And this is what it's trying to say right here. This is what this statement is talking about right here. If we were to think about, so these are going to be my even terms, these are going to be my even x terms, and these are going to be my odd x terms. So if you look at that, I should say my even interior x terms, and these are going to be my odd interior x terms. So when you look at this, right, if I were to write this, 0 would be, coming over here, this would be x0, this would be x1, x2, x3, x4, x5, x6. Okay? So my even terms, x2, x4 that are in interior are going to be multiplied by 2. Okay? And is that the case? 2/3 is multiplied by, f of 2/3 is multiplied by 2, and f of 4/3 is multiplied by 2. My odd terms, my odd x values are going to be multiplied by 4. So the ones that are in the interior, x1, x3, and x5. And that's what you see here. x3, x1, which is 1/3, x3, which is 1, x5, which is 5/3, are all, those function values are all multiplied by 4. And I'll let you plug those values in. I'll just tell you what the answer is. When you plug this in, you get the answer to be 4. Get the answer to be 4. You get the exact value. And the reason why you get the exact value is because remember that error that we had for Simpson's rule. The error that we had for Simpson's rule said that your error is going to depend on the fourth derivative of your function. Your error is going to depend on the fourth derivative for your function for Simpson's rule. That's what it said. The fourth derivative of your function is where your error is going to come from. What is the fourth derivative of x cubed? What is the fourth derivative of x cubed? The fourth derivative of x cubed is 0. It's 0, so therefore there will be no error for Simpson's rule for x cubed functions or cubic functions. Cubic functions will, if you use Simpson's rule for cubic functions, you'll always get the exact value. Although Simpson's rule comes from a second degree Lagrange polynomial. We're using a second degree Lagrange polynomial, but this approximation is so good that it works for cubic as well. All right, so we're going to stop right there and we'll pick up next time with some more interesting stuff.